Hello, welcome back to Extraterrestrial Resources. Today, we are going to look at the third part of this course. In the previous lecture, we have seen how elements condensated according to temperature across the protoplanetary disk. We have seen how planets formed, and in the rocky planets, how elements were distributed within the planetary body according to density. Today, we are going to look at that in more details, and we are looking at the distribution of elements in the rocky planets. I will talk about Mercury, Venus, and Mars. You have seen the distribution of elements on Earth in a previous course, I guess, and I will leave the resources of the Moon for the last part of this course, the part 4. We will look at the resources of the giant gas and icy planets. We will look also at the resources in asteroids and comets. So the rocky planets, they are located in the inner part of the solar system here. And the first one, close to the sun, is Mercury here. We don't know much about Mercury. It hasn't been probed much, but what we know, it has a very big metallic core, 60% of the volume. That represents about 75% of the radius. So if you remember what I said in the previous lecture, in the core of the rocky planets, we expect to find the siderophile elements, iron, platinum group elements, tungsten, etc. So that could be an interesting resource. However, to access it, we have to drill a mantle which is between 500 and 700 kilometers thick. That means the resource is difficult to access on Mercury for the moment. That's a real challenge for the moment. The next planet is Venus. We don't know much about Venus as well, because it has a very thick atmosphere. The temperature on the ground is quite high, about 460 degrees Celsius, and there is sulfuric acid in the atmosphere. That means the probes cannot see through the atmosphere, and landers have a hard time on the surface. The Soviets tried to send landers on Venus. They sent 10 landers, and they survived between a few minutes and 127 minutes only. So we don't know much about Venus. The few we know is that there is a volcanic activity, so we expect formation of magmatic ore deposits. And as I said, we have a thick atmosphere. 96% of this atmosphere is carbon dioxide. So that could be used for plants. That means agriculture. And we expect hydrothermal processes and chemical weathering of the rocks at the surface. That means we could expect concentration of valuable elements. But that is still hypothetical because we don't have the information for the moment. Next rocky planet is Mars. Mars is quite similar to Earth. It has a metal core formed by iron and nickel. It has a mantle formed by silicates, a crust formed also by silicates, and most of the surface is covered by basalts. We have a magmatism which is younger than 200 million years. So because we have magmatism, we expect formation of ore deposits, but we have also a thin atmosphere. That means we have weathering of the rocks on the surface. And that led to formation of iron oxide on the surface of the planet. That's this red aspect, this red color of the soil you see on these two photos from the Martian soil. And that is low-grade iron ore. We expect also to find metals and valuable elements in the rock-forming silicates of the crust and the mantle. The space probes have identified a localized concentration of hematite, which is an iron ore as well. We have olivine from basalts at the surface. Olivine is a manganese iron silicate. So we expect there's elements to be found in reasonable concentration. We expect also to find nickel and cobalt in olivine. The space probes have also identified water ice on Mars that is very useful for colonization of the planet. And the thin atmosphere contains 95% of carbon dioxide. That is, again, useful for plants and agriculture, and that could be also used to produce methane as a rocket propellant. So that is the resources we expect in the rocky planets. So we can switch to the giant planets. And this is this group of planets. We have two subgroups, the gas planets, Jupiter and Saturn. They are formed they have a very thick atmosphere. There is, in majority, hydrogen and helium. On the second subgroup of planets, icy giant planets, Uranus and Neptune. We have hydrogen and helium in the atmosphere, but we have also water, ammonia, and methane in the icy mantle of the planet. And again, methane and hydrogen can be used as rocket fuel. The giant planets have moons, Jupiter moons here, and on these moons you can find water and oxygen. In the Saturn moons, here same thing, oxygen and also nitrogen. So plenty of volatiles as resources in the giant planets. Now we can go further out in the solar system, and that is comets and asteroids. They are the leftovers of the planetary formation. If we look at the comets, first they come from the Kuiper belt, which is an asteroid belt here beyond Neptune. And the comets are between 100 meters to 30 kilometers across. You see an example of a comet, 4 by 4 kilometers. That's the picture of the Halley's Comet. And their composition is basically rock, dust, and ice, mostly volatiles. That includes water, carbon dioxide, methane, and ammonia. The problem with comets, we don't know much about them. They are obviously difficult to investigate. We need to send very specific space probes. So we don't know the composition of them in details. As a resource, if a comet wanders close to Earth, we can expect to capture it and use the valuable elements. What is more interesting, that's the asteroids. We find them in two locations, Kuiper Belt and the so-called asteroid belt between Mars and Jupiter. They are small bodies compared to the planets, but they are up to 1,000 kilometers across. On this figure, you see the 4 largest asteroids. They come from the asteroid belt. As a matter of comparison, the moon diameter is 4,574 kilometers. That's about 4 times the diameter of Ceres. From what we know about asteroids, we believe they have undergone little change since their formation, and they formed at the same time of the planets. And they have been investigated by space probes and telescopes, Earth-based telescopes. And based on the emission spectrum of elements, basically how elements reflect light, we can distinguish 3 compositional types or spectral types using the Tollens classification. C-type asteroids for carbon-rich and silicate-rich asteroids, 75% of the total asteroids. S-type asteroids, silicate-rich, about 17% of asteroids. And finally, the metal-rich asteroids, M-type asteroids. C-type and S-type can be grouped as stony asteroids in opposition to metal asteroids. Again, from the data we have, the information we have about asteroids, we think they experienced different stages of planetary differentiation. Some of them could represent crust and mantle of planets. Some of them could represent cores of planets. And we believe they are remnants of shattered planetesimals. In fact, most of the information about the composition of asteroids comes from the study of meteorites. The meteorites, we believe, are fragments of asteroids from the asteroid belt, and their chemical variety indicates they were parts of larger planetary bodies. They consist essentially of nickel-iron alloys, silicates, mainly olivine and pyroxene, and some of them are formed by a mixture of them. Many system of classification for meteorites, but to keep things simple, we can group them as three types. The first one, aerolites or stony meteorites. The silicates are more abundant than metal, and we believe the parent bodies of these meteorites are stony asteroids. The second type of meteorites, the siderolites or stony iron meteorites, 50% metal, 50% silicate. The parent bodies are probably some stony and metal asteroids. Finally, the third type of meteorites, siderites or iron meteorites. They contain more metal than silicates, and their parent bodies must be metal asteroids. So let's look at in details about these meteorites to assess the resources in asteroids. First, the stony meteorites. They can be further divided into two groups. The first one, the chondrites, they represent 85% of all meteorites found on Earth. Their average composition is about 40% of olivine, 30% of pyroxene, and 10% of plagioclase. We can find between 1 and 20% of nickel iron alloys and 6% of troilite, which is an iron sulfide. That's a picture of chondrite, and they are named chondrites because they contain chondrules, and this is what you see here. Most of the chondrites, the chondrules, are formed by olivine and pyroxene. They are not all like this one. We have some variating, and this one has a completely different aspect. We have a large part of it formed by olivine, pyroxene, and plagioclase, and scattered across the rock. We have sulfides here. So stony asteroids, which are the parent bodies of these meteorites, could be suitable prospects for resources if they contain in enough proportion sulfides. Next, we can go to the other type of stony meteorites, the achondrites. They don't contain chondrules. They are more or less the equivalent of crust and mantle of rocky planets. So an average composition of pyroxene, olivine, and plagioclase, negligible amount of metal. But because we have a significant amount of olivine, we can expect manganese, nickel, and cobalt in few percent in terms of composition. Magnesium and iron, probably about 45% of the composition of olivine. So that is highly dependent of the proportion of olivine into the body, the parent body. Pyroxene contains chromium, nickel, scandium, and vanadium in few hundreds of parts per millions or ppms. That's about 100 times smaller than a microgram. In pyroxene, we have about 15% of iron and magnesium in terms of composition. We have about 1 to 2% of titanium. So again, that is a potential resource, but depending of the proportion of pyroxene in the rock, in the asteroid, plagioclase could be found. It contains strontium, barium, and rubidium in few hundred ppms. So as a summary, we are talking about low-grade ore for achondrites. The next type of meteorite, the siderolites, stony iron meteorites. They are made up by nickel and iron alloys. We have silicates in approximately equal amounts. And we can distinguish two groups of siderolites, the pallasites. They are the equivalent of the crust mantle boundary in rocky planets, and mesosiderite, and they are what we call impact breccias. They are basically a pile of rubble stick together, and we believe they are remnants of collisions between partly molten planetesimals. In details, first, the pallasites. They are made up by a continuous matrix of nickel iron alloys. This is what you see in this picture. And this matrix encloses grains of centimeter size olivine. This is what you see here. And we can also find phosphates and sulfides as minor components. In terms of composition, pallasites are very interesting in terms of resource. They contain between 40 and 60% of iron. They contain a lot of other metals and elements. And here you see the composition of the average pallasite compared to the upper crust of Earth. This is the section of Earth we have access. And you see in pallasites, nickel reach 11%, and this is what we get in the crust of Earth, 0.0047%. Pallasites are also very enriched compared to the crust of Earth in cobalt, 6,000 ppms, chromium, 100 ppms, gold as well, 2 ppms compared to 1.5 ppb, part per billions. That's 100 times, that's 1,000 times smaller than ppm. We have also platinum, 4 ppms compared to the 0.5 ppb in Earth's crust. Germanium, 49 ppms. Germanium is a very useful element for optic fibers, optics, and solar cells. Iridium as well, very enriched compared to Earth's crust. The mesosiderites, the metal phase is discontinuous compared to the pallasites, and the silicates are mainly olivine, plagioclase, and pyroxene. In terms of composition, iron represents between 24 and 50%. Metal is here on this picture, and the silicates are here. Again, we can compare the composition of average mesosiderites with the upper crust of Earth. Nickel is also very enriched in mesosiderites, 7 to 10% in composition. Cobalt, 1,200 ppms. Chromium, almost 6,000 ppms. germanium, iridium, also very enriched, gold, and molybdenum. From the investigations of mesosideриtes, we believe that the origin of these meteorites is the asteroid Psyche. It's an M-type, metal-type asteroid formed by 95% of metal, nickel and iron, and 10% of silicates, mostly pyroxene. So that's good stuff for resources. Then we can switch to the third type of meteorites, the siderites, iron meteorites. And this is one nice piece on display at the Swedish Museum of Natural History in Stockholm. They are considered as representative of the chemistry of the cores of the rocky planets, and their parent bodies are the M-type, metal-type asteroids. In details, they are formed by iron-nickel alloys, pallasites, and tianites. We can find also troilite, iron sulfide. Phosphates are also present, and graphite. Iron, nickel, and cobalt make up more than 95% of the composition. The nickel content is between 5 to 25% of the composition, always present. That is very, very interesting in terms of resource. So if we cut a piece of iron meteorite, this is what we see. You have the Cape York meteorite in the Swedish Museum of Natural History in Stockholm. In details, this is what you see. That's the iron nickel alloys, and here you have troilite. They are characterized by this pattern, the Windman-Stetten pattern. It's a intercrossed texture of lamellae of nickel and iron alloys, the pallasites and the tianites. Both of them contain a lot of iron and nickel, as you can see. So very, very interesting in terms of resource. If we look at the trace element compositions of iron meteorites, I give you the example of this meteorite from Czech Republic. And we can compare with mesosideриtes and pallasites, and again with the upper crust of Earth. A lot of cobalt, 5,000 ppm. Chromium is not as abundant as in the mesosideриtes or pallasites, but still more abundant than on Earth, on at least the crust. Germanium is as abundant as in mesosideриtes and pallasites, more abundant than the upper crust of Earth. Molybdenum, quite slightly more enriched compared to mesosideриtes. But what is interesting is lanthanum, a rare earth element, 200 ppm of it compared to the 31 ppm in the crust of Earth. The iron meteorites are very enriched in platinum and other platinum group elements, 13 ppm compared to 0.5 ppbs in the crust of Earth, 4 ppm only on pallasites, so much more enriched in iron meteorites. Iridium as well, very more abundant compared to other meteorites and the crust of Earth. Gold, slightly less enriched compared to pallasites, but more abundant definitely than in mesosideриtes or the upper crust of Earth. All the rare metals expected in the core of rocky planets are abundant in our iron meteorites. That is very, very interesting in terms of resource. I give you just an example for the platinum elements group. Here we have the concentration of rhenium and osmium in different in meteorites, the mantle of Earth, different magmatic rocks here, the continental crust, sediments, and ore deposits. And in fact, for rhenium, the iron meteorites are as abundant in rhenium as molybdenite, that is rhenium ore, basically, or sulfides. Same thing for osmium. It's osmium content in iron meteorites is equivalent to what we expect in sulfides. So basically, the content of platinum group elements in iron meteorites is the equivalent of world-class ore deposits on Earth. The main difference is that the ore deposits on Earth, they are only a few kilometers in size for the biggest, but in the asteroids, it could be 100 kilometers big. So we have much bigger resource available in asteroids than on Earth. To illustrate a bit further the interest for asteroids in terms of metals, you have the composition of this asteroid here in terms of metals: iron, nickel, platinum, and cobalt. The value of these metals in 1994 and now in 2012. That means in the future, if the resources, if the elements are getting rare, the value of these metals in asteroids will increase. As a summary about the asteroids, the parent bodies of stony meteorites, the stony asteroids, are rather low grade ore. We need to process a lot of material to get few ppms of valuable elements. The resources, they are mainly for nickel, iron, magnesium, few percent available, but we can find also titanium, scandium, vanadium, chromium in terms of a few hundreds of ppms. That means we have to prospect carefully the asteroids to find the right targets, and we need to focus on big asteroids. On the other hand, iron and stony iron meteorites, parent bodies, that means some metal-rich and stony and metal types of asteroids, they are the main targets to get resources. And we are talking about large amount of them. We are talking about iron, nickel, chromium, and cobalt, germanium, gold, copper, molybdenum, and platinum group elements. They are really abundant in iron and stony iron types of meteorites, and then their parent bodies. And that will be it for part 3 of the course.